Hi there. So this is the second lecture for the course Trustworthy AI. In the previous lecture, the first one, we looked at fundamentally two questions in the broader sense of trustworthy AI, where we talked about what it takes, what it means to be uh, trustworthy for machine learning, and what also it should take to truly make advances in trustworthy machine learning. Today, we're going to do basically a crash course on deep neural networks. This is meant for people who are following this course, but may not come with, let's say, the foundational background on deep neural networks or generally machine learning. So, as I said in the first lecture, this is not a machine learning course, but we're going to talk about machine learning throughout the course. Therefore, it helps to fill that gap of any background or deficiency where people may not be well versed in the fundamentals of deep neural networks. So the focus here is on deep neural networks because the tool of the day, as far as machine learning goes, is some variation of deep neural networks. Therefore, it helps to have a good grasp of what or how this machine learning models work. So more specifically, we're going to look at first an overview of supervised learning. So I'll be brief on this one, and then I'll spend most of the time talking about the building blocks of neural networks and how we actually build and train neural networks, and some important considerations on doing this in practice, like training deep neural networks in practice. And at the end, we'll also highlight this important phenomenon in machine learning called overfitting. Okay, so let's dive in. So supervised learning. So machine learning could be broadly classified into three categories: supervised machine learning, unsupervised machine learning, and reinforcement machine learning. And you could get different variations of these classifications if you look at different literature or textbooks, but roughly that is where we are. So throughout this course, we'll consider mostly about supervised machine learning and specifically for tasks aimed at doing classification. Because in supervised machine learning, you can also do other things like regression. So the setting is you're given a training data set, let's call it D, which has n number of data points, and where each data point is a pair of the feature vectors and the corresponding labels. So by definition, in supervised machine learning, you have labeled data sets. And this individual data points, the feature vectors, they do have some dimension D. So the dimension D here refers to how big a feature vector is going to be. And the dimension N here is talking about the number of data points I have in my training set. And then the Y is actually a set of labels, and you oftentimes designate this using K as the number of labels or the number of classes. So what you see down here is an example of one of the benchmark data sets in the computer vision domain, specifically in image classification. And this data set is called CFAR10, simply because it has got 10 classes of different images like airplane, automobile, bird, etc., all the way down to truck. And if you simply look at this data set, as you see it on this slide, the number N is 100 because I have 10 samples from each class, and the number of classes is 10. And the actual dimension of the individual images in the actual CFAR10 dataset is 32 by 32 pixels. And we do have three channels, the red and green and blue channels, or the so-called RGB channels for each image, because as you can see, the images here are colored. Okay, so this is the setup for supervised machine learning. And in supervised machine learning, the goal in our case here is classification. So the goal of this training is fundamentally function approximation. So we're going to approximate a function f parameterized by what we call a weight vector. And this weight vector would have the same dimension as the input vector. such that the ultimate goal is we expect F to perform well on a new input X that it has not seen during training. So in short, what we're trying to do is we want to compute this value Y hat that we call a prediction as a function of the trained model given an input on based on the parameters or the weights of the model. So what we wish in the most ideal case is we want this estimate Y hat to be a good estimate of the ground truth. So if I go back here, if I give it an image of a bird, I want this Y hat to be to give me the label of the label bird. Okay, so that's what we mean by a good estimate. And during training, to kind of grade the machine learning model as it evolves and learns when it looks at a lot of data, we have to check whether the machine learning model is heading in the right direction, namely becoming more and more precise on detecting these inputs. So for that, we use a metric called loss function. So the loss function, which we usually denote using J or L, is a function of the weight. So basically, the purpose of the loss function is to measure this notion of what I called performance well earlier. So how good is the model doing or how bad it is doing? When the loss is low or zero, it means the model is doing well. When the loss is higher, the model is not doing well. Therefore, we have to probably take some actions to make sure that we direct the model in the right direction where the overall loss is going to be minimal. So the ultimate objective in supervised learning when you train a model is basically minimizing this loss as with respect to the weights of the model, such that the final function that we approximate, given an input and the final weight that it is as learned, is good on the dataset D. And the training goal, as I said, is basically computing this set of weights that minimizes the loss function. And the loss function could be computed in different ways. And there are a whole bunch of functions that you can use. But here is an example of loss function. This is what we call the mean squared error in statistics, which basically is doing the average loss of the function or the model F in this case, given the actual value yi, the actual label yi, and the predicted label. So this is the actual label yi or the true label. And this is what the model has predicted based on what it has learned so far. And when you do the mean square average of the mean square error of this over the whole data set, because the number n here indicates the overall data set we have, you will get a sense of the aggregate or the average error rate of or loss of the model. And that would give you as to where the model is heading. And to expand on f of xi given w, the way you're going to compute this is basically a dot product between the weights and the input vector. And the reason why we said earlier that the xi is of dimension d and the weight is also of dimension d is simply because when we do the dot product here, we have to have a symmetry between the dimensions of the weight and the input vector. Okay, so that's basically a high-level idea of what a supervised learning algorithm is doing, regardless of what the algorithm is, what the data set is, what the loss function is, and what the dimension of the input and other variables are. Okay, so hopefully that gave you sort of the bird's eye view of what a supervised learning algorithm does. Okay, so keep that in mind. And we're going to expand a little more on this one when we talk specifically about neural networks. Okay, so now, before I introduce the building blocks of neural networks, what is the big fuss about, neural networks? Because everybody talks about them. every useful model or every model that is making a headline today is somehow powered by some variation of neural networks. So here's what we have. So in traditional machine learning, so by this I mean, the classic machine learning models that are not neural networks, but they are still helpful to do a lot of useful work or useful a lot of classification tasks. These models are models like decision trees, random forests, support vector machines, Bayesian classifiers, and a whole range of others like logistic regression. Traditionally, these models, for the most part, require manually doing feature engineering. So the features are computed manually, and this process is pretty slow. It's a very daunting task. And this traditional ML algorithms also tend to be very brittle because the features are computed manually, and it depends on who computed the features, what features you pick, and how representative they are, how discriminated they are, etc. And as a result, this traditional ML approach may not scale. So what is going on in the world of neural networks or in the modern day machine learning is, instead of manually doing feature engineering, we're trying to automatically learn representation from raw data. For example, given images, you go down to the smallest units of image representation, namely pixels, and start from the pixels and hierarchically learn useful structures within that image. So here is an example where I illustrate this process of representation learning from images. Okay, so suppose your goal is to learn a model or to train a model that does, let's say, facial recognition. So given a face of a person, we want to identify that person. Okay, so this could be used for facial recognition-based authentication and things like that. So the way this is going to happen is in the sense of representation learning. You start with the smallest basic structures or building blocks. In this case, you might have to start with lines, curves, edges, and so on. This are called low-level features. And then you go to the next level of abstraction or the next level of granularity. In this case, you would learn these individual substructures that on their own are meaningful, but collectively are very powerful to define a specific structure, like a facial structure. So in this case, for instance, for the image case, you get to this intermediate level features called, for instance, eyes, nose, ears, and other structures, things that you see on a person's face. And eventually, you end up with an abstraction or a representation of what you consider to be a model or representation for a facial structure. And that would be the basis for learning or classifying different faces into different identities or individuals. Okay, so that's the key power of modern deep neural networks as compared to traditional machine learning. And that seems to be the most important capability that neural networks are bringing into into this pervasiveness of machine learning in our life. Okay, so with that background, now let's shift our focus to the building blocks of neural networks, because today you can, within an hour or maybe less, you can go to an open source library of, let's say, Google TensorFlow or PyTorch and others, and you can train a machine learning model like a neural network, a moderately complex neural network, and you might end up with the whole pipeline, and you could be impressed. But it would be useful to kind of understand how these models that we easily train today came about. And it helps to kind of get the foundations right. So a perceptron, what is it? A perceptron is actually the building block of any neural networks that you see today, whether it is a simple image classifier or a generative model that seems to be doing magic today. the building block is this notion of perceptrons. So what is a perceptron? So I do have a representation or an illustration of a perceptron here, but let me just give you first the description. So a perceptron is actually a decision function. It's nothing, it's a decision function that is loosely inspired by biological neurons. Okay, so the neural networks that we use today have their inspiration drawn from how our brain functions, and specifically how neurons communicate or fire signals or send messages to one another. Okay, so in a way, mathematically speaking, this is a decision function. So if it is a function, it must have inputs. It must do some processing. It must produce some output. And we might have to do further processing on that output to get something that is useful. And that's exactly what is going on in the modern day neural networks. So it is a decision function. Next, what you see here are the feature vectors of an input. So if you have, let's say, an image that is a 4x4 pixel image, then you've got 16 dimensions. So the D here is going to be 16. So you just flatten the image across by multiplying the dimensions, and you will get like a single vector, which would end up the input or the feature vector. And what we have next is what we call weights. So every input, every dimension of the input or every feature vector is going to be attached to this summation function, which is actually the perceptron function, the decision function, with some notion of weight. And this idea of weight is simply to attach how important each dimension of the vector, the input vector, is to contribute to the final decision. And this is the most important learnable parameter, the set of learnable parameters in the learning process as a whole. The ultimate goal of training a machine learning model in a supervised fashion is to end up with a set of weights of the same dimension as the input that would best approximate the characteristics or distribution of the data and captures the logic behind how to classify inputs. The summation function here is basically the sum of the products of the weights, the W's, and the X's, or the feature vectors correspondingly. And in short, this is a dot product. And then after that, we have the output of the summation function. Now we have this function called G, and this is what we call the activation function. The activation function, I will give you more insights into why and what it is, but roughly speaking, it will create what we call non-linearity to the model. And once we pass the summation through the activation function, we get the output. Let's call it y hat, which fundamentally is wrapping the activation function around the summation of the summation function's output, which is basically the sum of the products of the individual elements of the weights and the input vectors, plus this other term called the bias or the threshold. The bias, as its name indicates, it helps in shifting the decision boundary, and it's also one of the learnable parameters. So in the space of supervised learning, as the training progresses, the changes that would happen to the model are on the weights and also on the bias. So at the end, we'll have the final version. When we finish the training, we'll have the final version of the weights and the bias. Together, the two would create our function or decision function that we would use to classify new inputs. And when you have to compress this, you can write it as G of the dot product between the weight and the input vector plus the bias. And the only reason why we are using X transpose or the transpose of the the input is simply because when we do matrix, because this would translate practically into matrix multiplication, and the multiplication, as you know, when you multiply two matrices, you have to have a match between the column dimension of the first matrix with the row dimension of the second matrix. So that's why we have to do a transpose here. Okay, so that's fundamentally what a perceptron is and what the different parts of a perceptron are. And as you will see, understanding this fundamental representation of the building block of a neural network, you can basically understand almost all complex neural networks that we have today. Okay, to just make this a little more concrete, here is an actual example. So suppose you have an input which has a feature vector x1, x2, x3, and I'm using x0 or x0 here to capture the bias. And here are the weights, and to have the summation function and the activation function here. So x is 2 minus 1, 4. That is what we're given for the feature vector. And w is 1 minus 2, 3. And we do have 0.5 for the bias. So basically what you compute is y hat, which is the activation function applied to the dot product between the transpose of the input and the weight vector plus the bias, and that would end up with this number. Okay, so in programming languages like Python, where most of the machine learning libraries are today, you could implement this in a very simple fashion. So you take the NumPy array, the NumPy package. So in NumPy, you can basically create a NumPy array for the weight and the input vector, and you have the bias here. And you can apply an activation function. There are a whole range of activation functions. In this case, the activation function that we're using is called the sigmoid activation function. So y hat could be computed as 1 over 1 plus e to the power of z, where z is our whatever we're passing to the activation function. In our case, our z is the dot product of the weight and the input vector plus the bias. Okay, so I was talking about this function called activation function, which happens to be a very important piece in training neural networks. So the activation function I used earlier is called the sigmoid function. And what is special about this activation functions? The purpose of the activation function is to actually ingest a value and then produce a value that is in a controllable range. For instance, the sigmoid function, given any value, z, it would compute a value between 0 and 1. So as you can see here, this range is between 0 and 1. And this is very useful, especially in situations where you have to predict the probability distribution of inputs, okay? Because it sits well between 0 and 1. And what you have as g prime is just the derivative of these functions. And the fact that this activation functions are differentiable is also a very important property in making a choice here. Another common activation function is what we call hyperbolic tangent, or tan h in the libraries. And again, it does the same thing, except that it produces an input between 1 and minus 1. It produces an output, rather, between 1 and minus 1. And this might also be useful in some situations. And another example is this widely used activation function called rectified linear unit, or ReLU. The ReLU activation function actually produces the output would be the maximum between 0 and whatever input you give it. So the upper bound here is, there's no upper bound, but the lower bound is clipped at 0. Okay, so for now, just keep in mind that being differentiable is a very important property of activation functions. Okay, before we leave activation functions, I mentioned earlier that the purpose of the activation function, if we go back here, the purpose of the activation function is to introduce non-linearity to the model. What do we mean by this? So if you think about the way we're computing the final prediction, which is the dot product of the weights and the input plus the bias, right? That is pretty similar to the notion of linear equations that we know in linear algebra. But in real life, a deep neural network, although it is piecewise linear, like we see it here, if you take one piece or one neuron or perceptron, it's a linear equation. It is simply apply the activation function on the sum of the product plus the bias. But in real life, data distribution is pretty complicated, and it's oftentimes nonlinear, right? So that is the reality we live in. And as a result, when we use activation functions, we want to make sure that these activation functions reflect the reality we live in and the nature, the actual nonlinear nature of data sets in real life. So what you see on the right here is sort of an illustration of what I'm trying to say. So suppose you have this green and red dots or points, right? So your goal is to approximate or to come up with a function that would separate these two classes, the green and the red. As you can see, with linear models, it's really tough to kind of come up with a line that would cleanly separate. So instead, what you would do is you will have to think about a decision boundary that would capture the boundary or the difference between these two data distributions of two classes, such that when you try to use this model later on, it will perfectly or almost perfectly classify inputs to the right class. So maybe what I am drawing right now is the perfect classifier or decision boundary. But with linear models or linear representations, as you can imagine, this is pretty difficult. So that is fundamentally the reason why we apply activation functions and the reason why activation functions add nonlinearity to the intermediate computations that we have as we train. Okay, so I hope that gave you sort of the foundational idea of what a perceptron is, what the different parts are, and why we do things like activation functions, etc. Now, I think we can use the building block, the perceptron or the neuron, to gradually build deep neural networks. Okay? All right, so now I'll give you an example where we have a deep neural network with two hidden layers. So between the input layer and the output, which is essentially the dimension of the output layer, would be as many as the number of classes that you want to predict. For example, in this case, we have two, and that means we have a binary classifier. So our input layer has got x1, x2, x3, x4. So it's a feature vector of dimension 4. For sake of simplicity, I avoided the bias, but also in the back of your head, imagine the bias is also added somewhere over here, right? So you can think about the bias here as x0, right? Like we did it in the previous example. And it's going to be attached to all of this, right? Okay, and so on. So keep that in mind. I'm just trying to make this simpler and try to convey the basic ideas without getting deep into the complexities of neural networks. Okay, so we have an input layer, which is basically the representation, the feature representation of the input, and the output layer. In between the two, we have to compute this intermediate or hierarchical computations to make sure that we capture this intermediate layer abstractions of the input that is being transformed through this neural network. So this actually goes well with what I was talking about earlier on this slide, which is we start from this, the basic building blocks of the input, and we hierarchically or one layer at a time get to learning the actual structure of a face. So it's exactly that that is happening over here. So this layer, how many layers to have and the size of the layers and so on, there is no like magic formula for this, but depending on the data set, the data distribution, and many other things, and many other factors, you can play with this. So there is sort of a relative freedom as to how you can deal with this, but also there is also best practice for depending on the data. But in general, the general takeaway for you here is the middle layers that we call the hidden layers are here to capture that hierarchical representation learning as we go from the input to the output layer, where the final numbers that we compute at the output layer are indications of the probability that this input belongs to one class versus the other in this binary classification. And also notice the fact that the computations are layer by layer, and the information is fed forward. So for instance, in hidden layer 1, so this layer over here, the way we're going to compute the HIs here, if you pick one of the HIs here, or one of the nodes, the values of the nodes here, it's going to be, of course, we always apply the activation function G, and the same way we did for the perceptron, we just have to aggregate them now. So J runs from 1 to 4 because we have 4 inputs, and we have to do the product between the weights that go to the 5 inputs, right? So if you pick one of the edges here, there are 5 edges coming from each input. So that is the I value, which is 1 to 5. So you're going to do the product of Wij at layer 1 multiplied with Xj plus the bias at that layer, bias I at that layer. You do the same thing for others, except that you just have to do it for as many nodes or units you have for each layer. For example, for hidden layer 2, the I runs from 1 to 3 because I have 3 units or 3 nodes. And the output layer is going to be the same way. So I have 2 units or 2 nodes, and you apply the same idea. And as you can see, what is within this G function G, what is going to the function G, the activation function G, is the sum of the products of the weights and the inputs multiplied with the bias and the inputs. And also notice the fact that the inputs at a particular layer is coming from the previous layer. So for instance, if you are at hidden layer 2, the input is Hj coming from the previous layer, and the weights are also coming from there. So this is basically how you compute. And as you can see, it's not as complicated as you might imagine. And this is fundamentally doing the perceptron computation over and over in a hierarchical fashion, one layer at a time, and feeding the information forward until it gets to the output layer. Okay, now that we have a good idea of how a neural network would be built and how the internal computations of a neural networks happen, let me give you a simple example. So suppose we have this ML task, which is a binary classifier that, given some data about a person who is applying for a loan, let's say this is mortgage loan, and we want to train a model that outputs 1 to approve or 0 to deny based on, let's say, for now, 2 features. So we have X1, credit score of the person or the customer, and X2 is the down payment percentage. So how much down payment they're willing to pay or they're capable of paying. So if you imagine plotting this data points, so the red boxes here are on the denial side, and the green boxes are on the approval side, right? So because when you look at the X1, the credit score, and X2, the down payment percentage, the green boxes are on the high side for both, while the red boxes are on the lower end. For example, most of them are below 500, and the X for the credit score, and the percentage of the down payment percentage is also less than 20%. But for the green ones, it's much higher. Okay, so suppose you've got this new data point. So suppose you trained your model, and this is what it looks like. So basically, this is going to be your decision boundary, roughly speaking, okay? Now, you get this point, data point, which is 550 on credit score and 14% on down payment. So that would roughly land over here. And you would see that this, by visually looking at this model, you would say, okay, this percent is going to be approved because the data point is almost inside the green region. Okay, now, so how do you compute the loss? We talked about the loss, right? So how do we compute the loss? Given the same example I gave you in the previous slide, as we know, the loss measures the cost that we incur when the model makes mistakes, right? So given x1 and x2, x1 is this value, and x2 is this value, right? And suppose we have this simple neural network, which has one hidden layer of 3 units, and this is going to be a probability that this is the loan is going to be approved or denied. And suppose this value is between 0 and 1. So when your model predicts 0.15, and the actual is 1, simply because we know that in the previous slide, we know where this lands, and it safely lands in the green region, right? So when the actual is 1 and the predicted is 0.15, it is an indication that the model is not a good model. It's not reflecting what the actual label is. So the way we do this is yi is the actual, so in this case 1, and the predicted one is you pass the function, the input, in this case x1 and x2, and also the learned parameters of the model, and you compute the loss. So the loss is going to be fundamentally the distance or the difference between what is the actual label and the predicted. You can also, so the example I gave you here is computing loss for one instance or one data point. But in real life, we deal with a lot of data. Therefore, we have to look at what we call empirical loss. And this is basically total loss over the entire data set, or the average loss over the entire data set. So the way we compute loss is, so suppose we're given this, right? This samples, and we compute the corresponding predicted values, and we also know the actual values. So the actual values are over here, and the predicted values are going to be this ones, okay? That's how you compute the predicted. So the empirical loss is basically the average loss over the whole data set, given the actual labels and the inputs, the actual labels and the predicted labels. Now, so as you can see, on this instance, the prediction is fine because it predicted 0.7, which is close to 1, 0.2 close to 0, 0.1 way far from 1. So this is going to be wrong, right? So this is basically the mistake that the model made. So if you look at only this 4 instances, right? If you look at this 4 instances, it means that out of the 4 predictions, the model made a mistake on 1 of them. So the loss is like 0.25. Okay, so basically this is the notion behind empirical loss or aggregate loss given a data set and a model. In practice, we have different classes of loss functions. One of the most widely used is what we call the cross-entropy loss. Cross-entropy loss is of a loss function that is suitable for models that output probability distributions like most models are in practice. So the loss calculation function based on the probability, based on the probability distributions using entropy, the notion of entropy. So the log here is the entropy idea. So what is happening here is you're going to compute, it's the same thing, except that you do the predicted ones over here. And you also have the predicted over here. And the actual ones are here. Okay, so there's a color matching. And again, this is, so you do the negative log likelihood as we do it in Shannon entropy. The idea is pretty similar. And you do it on average to compute the loss. So this cross entropy loss is a pretty common one. Okay, so that's about loss, and there are other loss functions, but for the sake of this lecture, I think this much is enough. All right, so now we know about the building blocks. We know how to build a neural network. We also know what a loss function is and how loss is computed per sample, and also on aggregate for all the data set, for like the test data set or the training data set. Okay, so how do we train? What actually happens when we train a machine learning model? As I said earlier, the singular objective in training a machine learning model in a supervised setting is minimizing the loss. So if you formalize this, it just comes down to an optimization problem, specifically a minimization problem of getting some version of the weights that minimize the aggregate loss or the average loss. So basically, it's an argument of with respect to the weight, using the loss function as the proxy for indicating how large the loss is going to be. And also remember the fact that the weight is something that we compute at each layer, as we saw in the previous example, neural network again. So to expand a little bit on this, when we do loss optimization, the loss, as we know, is a function of the model weights. So here is a demonstration of the loss landscape. Suppose for the purpose of this illustration, we have two weights, weight 0 and weight 1. So you have weight 0 and weight 1 in a two-dimensional space, and you're computing the loss on this weight 0 and weight 1. And you're plotting the actual weight, and what you see in this landscape is basically where the loss will be. So as you can see, this landscape is not that complicated, but you can see a lot of candidates for the what could be the minimum point or the minimal point of the loss. So using a loss landscape like the one I showed you earlier, the actual algorithm that powers machine learning today is called gradient descent. And gradient descent, the idea of gradient descent is to iteratively converge to the weights that minimize the loss. The goal is the same, minimizing the loss, but we need some algorithm, some systematic way of converging to that minimum location in the loss landscape, such that when we stop the training, we have a good sense of the model being accurate on new inputs. All right, so considering the previous loss landscape as an example, suppose you start over here, okay? So you start right here at this point. Once you start at this point, well, you compute the loss. So the algorithm is you initialize the weights randomly, for example, by sampling the weights and calibrating the weights. You sample the weights from, let's say, a random uniform distribution, and then you can do a little bit of calibration to make sure that the weight is not too high or too low. You start with that initial weight, and then you're going to loop until you converge. And within this loop, you're essentially doing two things. One is you compute the gradient with respect to the loss, with respect to the weight of the functions. You compute the gradient of the loss function, and the loss is computed with respect to the weights, of course. And getting this gradient value, you update the weights. When you update the weights, you update the weight by basically subtracting a fraction of the gradient that you computed. And you will see why this subtraction is important and what this fraction is, the eta here, the fraction is. And when you're done, basically when you know that you have exhausted your options, or when you know that you have looked at the data enough, and the model accuracy is not improving much, you would simply return the weights. Okay, so the way this happens, the way this function, this algorithm happens is, for instance, you start here with random initialization of the weights, and it lands you here. And then once you update, you go in the opposite direction of the gradient, and that's why the subtraction should be happening, because the gradient tells you the how much given a point, and when you compute the gradient, it tells you how much the function's output will increase. So the function being the loss function, you don't want it to increase, you want it to decrease rather. Therefore, you go in the opposite direction, and that's why we have this subtraction. And when you subtract, how much you subtract is controlled by this variable called the learning rate. And in our case here, we jumped from this point to this point. So that was the kind of jump we made. So that equates with the learning rate we use here. We jump to the next level, and we're heading in the right direction because we go to the lowest loss every time we do this gradient descent instead of gradient ascent. And we end up with, let's say, this final minimal point, which visually seems to be the minimum value for the loss. And we will freeze that the weight of the models at that loss to consider this model deployable or use it for actual predictions. Okay, so what I showed you here actually focuses on how the loss landscape is explored. But what I didn't tell you is on this one, when you update, what is actually, what does that mean? What is actually the act of updating the model? Okay, we have to go back. So we have to go back and update the individual weights of the model so that the model would be a better version of itself, right? So that idea is implemented or realized using the notion of backpropagation. So the idea is simple. So basically, we ask this question: how does a small change in one weight, let's say W2 in this case, here is W2, affect the final loss? Because at the end of the day, we want to estimate the contribution of an individual weight in the neural network to the final loss, to the aggregate loss, the average loss that we're computing. Okay, so that's the idea. So we have the final loss here. What is the contribution of any random weight? In this case, as an example, W1. And as you know, we start with the input. We have the weight one dimension, the weight one, compute the intermediate result, and then we have weight two, and finally we compute y hat, after applying the activation function. So you do this process repeatedly for every weight. So you got to be very exhaustive in the neural network using gradients from later layers. So basically, if you do so the way we compute the gradients is the derivative, right? So that's why we need this differentiability in the loss and the functions, in the activation functions that we use. So it's the derivative of the loss function with respect to the weights. So you start with the derivative of the weight, the loss function with respect to the weight vector, and you do that with respect to what is immediately before the weight, before the loss, which is the y hat, right? Multiply that with the derivative of y hat with z1 over here. So you're basically going backwards and do this multiplication until you get to the input. So you just stop right before the input where you have the weights in the first line. And this actually is called the chain rule in differential equations. So we're applying basically, so backpropagation is actually chain rule on steroids. So that's fundamentally what the backpropagation is and how you're going to basically sprinkle back this estimated values that would overall minimize the loss of the model. Okay, so that is fundamentally what is happening when we're doing the forward computation and the backward propagation in neural networks. All right, so in the final segment of this lecture, I'm going to talk a little bit about, okay, what are the considerations that we should be having when we talk about practically training machine learning models, specifically deep neural networks. So the landscape, the loss landscape I showed you earlier is fairly simple. And you can also visually inspect and say, maybe that is the lowest point in the loss landscape. But in real life, in very complex real life data, the actual loss landscapes are pretty complicated or complex. Here is an example of a CIFAR 10 dataset. So this is a dataset of 10 classes, as I shared with you earlier at the beginning, of images of different nature and colored images. And the overall data set is about 60,000 samples. So this visualization is actually the visualization of one variant of the CIFAR 10 model called the ResNet model, and one of the popular model architectures back in the day. And you will see the landscape is pretty complicated. And it's not that trivial to kind of determine that there is one single minimal point. There might be competing minimal points. If, for example, if the minimal point is right here, there are competing minimal points. And because the visualization is not absolutely showing the other side of the landscape, maybe there is another point on the other side of this loss landscape that is actually the, let's say, the global minimum. So it's really easy to be stuck in what we call a local minima as you navigate this loss landscape. For example, you start here randomly and you end up going, for example, this way, and you might end somewhere here in a pocket of the loss landscape, but that is not the actual global loss. So you might be stuck with the minimal, the local minima of the loss landscape. Okay? So that's a very serious problem in machine learning. There are some workarounds for this, but based on, for example, the kind of loss functions you choose loss functions for which they have some property like a convex property where the loss functions have one minimum point and so on. But it's still a very open problem as to how we deal with getting out of the local minima situation. Okay, so the other important parameter is the learning rate. I kind of highlighted what it means. It's basically the amount or the degree to which you jump from one state to the next stage in the gradient descent process. And how big this is going to be is going to determine how good your model is going to descend to the minimum point, if at all possible. So suppose you start at this initial guess, right? When you initially randomize randomly pick the weights. And then this is your true minimum. So you want to end up here if you want to end up with the minimum loss, the best case scenario, right? Okay. Now, you could set the learning rate too small. And when you do that, the model would converge very slowly. And it might have the problem that I was talking about. It might get stuck in a local minimum. For instance, in this case, you started with the initial guess right here, and you went updating the model. So you're descending. Technically, you're descending. But look at the number of iterations. 93. After 93 iterations of the gradient descent algorithm, you're right here. And the accuracy of the model is not improving much because the loss is almost flat around here. So you might mistakenly stop here and say, okay, this loss is not changing much. So let me stop here and declare that the model training is over. But as you can see, this is a classic example of getting stuck in local minimum because the true minimum is down here. And there is a huge difference between what you see here and what you find here for the loss. Okay, so that's the implication of picking too small magnitude for the learning rate. the flip side of this is, what if you pick a too large learning rate? You have the opposite kind of problem. So in this case, you start here and you might overshoot and diverge from the true minima. So you might basically miss the true minimum and land on maybe a worse spot, a very bad spot where the loss is pretty large. Okay. So you might wonder, okay, too small is too bad, too large is not any good, any better. So what is the middle ground? So the ideal case is when you converge smoothly to the minimum point. For example, in this case, in only 11 iterations, you end up getting to the minimum point. Okay, that's what we want to do. But this is not an easy, or it's not a trivial thing to do. Usually this comes down to some heuristics and some best practices. So how do we deal it in practice? The common strategy is you're going to try lots of different learning rates and see what sticks on the wall. But even a better strategy is to do this adaptive learning rate that adjusts based on some parameters. For example, how large the gradient is, the magnitude of the gradient is important, how fast the learning is happening, for example, how fast the loss is dropping, and the size of the particular weights that you are dealing with, and many other things. So there's, again, this is also one of the open problems for which we don't have like an exact solution, but we rely on best practices and heuristics like this one. Okay, so something that I didn't mention in the gradient descent is the fact that gradient descent, especially computing gradient per sample, is going to be a very expensive, computationally speaking. So we have to do something about this, or we will end up with a training process that will take forever, especially for large data sets that we train today with millions and billions of samples. So what is the solution? The solution is what we use in practice today, and it's called stochastic gradient descent. And the idea behind stochastic gradient descent is, instead of relying on a per sample gradient computation, we rather rely on per batch gradient computation, where a batch or a mini batch is a representative set of samples that we're going to randomly pick based on some smaller size compared to the training size. Okay, so we will pick a batch of size B, and we compute the gradient on that batch, which is much smaller, but representative of the data that we're dealing with. And we do the weight updates based on the gradient computed over the batch, which makes life easier in terms of computational overhead. So the benefit of mini batch-based stochastic gradient descent is we'll end up with a more accurate estimation of the gradient, and the convergence would be smoother, and we'll have this wiggle room or larger room for learning rate choices. And we can also benefit from the fact that the learning would be, or the training would be faster because of parallelization and efficient use of compute resources such as GPUs. Okay, and lastly, we'll talk a little bit about this phenomenon that you can't really skip if you're doing machine learning. It's called overfitting. So what is the overfitting problem? Overfitting is when your machine learning model is too complex and it ends up trying to do more than it has to do to fit the data that it's looking at. And as a result of this, it just fails to generalize. So here is an illustration of overfitting compared to what we call the ideal fit, which is, given this data set, would be ideal to have a model that cleanly fits the data and separates it into two classes, let's say. But we also have the other side, the flip side of overfitting, called underfitting, where the model is having a problem fitting the data, or it couldn't really fully learn based on the data. So overfitting is a big problem in machine learning, and you have to look out for signs of overfitting when you train machine learning models. Okay, so what are the solutions for taking care of overfitting? Overfitting is not something that we want to live with. We want to avoid or minimize as much as we can. So regularization has been one of the ways to deal with overfitting. So what is regularization? the idea is you want to constrain the optimization problem, the gradient, the stochastic gradient descent, to discourage complex models. So you need to do some smoothing of the decision boundaries that you're going to learn. And the reason is we want to improve generalization of the model on data that was not seen during training. So there are two common strategies. So there are many others, but I'll just highlight two common strategies. One is called dropout. So the idea of dropout is simple. When you do training, you're going to randomly switch off some units in the neural network or some neurons. For example, you set their activation values to 0. And the typical mechanism is to use some drop rate percentage, dropout percentage of activations in a given layer. And this would force the model not to rely on any single neuron or any group of neurons in a layer. So if you consider this example on the left, where you have this fully connected neural network, an effect of a dropout would be what you see on the right. So on the first hidden layer, I dropped this node and this other node. So this is like 50% dropout for this layer. On the next hidden layer, I dropped one of the 4, which is like 25% dropout rate. So that's how you basically implement or apply dropout. And this helps a lot in practical training. Another important step, indicator for overfitting is early stopping, or idea that you use. So this is basically, as it says, you stop the training before overfitting takes over. So if you look at this illustration, on the x-axis is the number of iterations or the number of epochs, and on the y-axis is the loss. So we're tracking the green curve is the training loss, and the blue curve is the testing loss. And what we're watching is the test loss, because the overgeneralization is manifested in when you do testing on the trained model. Of course, in the training world, things are pretty much smooth, and the loss just organically drops as we train the model with more iterations. So here is your turning point. Basically, up to this point, the loss was dropping. And then from this point on, as we train the model with more iterations, the loss is increasing. That is the place where you have to stop the training, and you live with whatever you have at that point, because it doesn't really help to go further because the loss would increase. Okay, so that's the idea behind early stopping. All right, so in summary, what we did in this lecture is we covered the fundamentals of neural networks in the broad sense of what we're going to be covering in the course. And we talked about this notion of perceptron, which is basically the building block that every neural network that we see today is based on. And we looked at how we can build, starting from the perceptron or the single neuron, how we can build and train neural networks. We talked about the notion of loss function, gradient descent, and how we can compute the loss, and how we can update the model, how we do back propagation, and all those things. And lastly, we emphasized on important nodes, considerations for training deep neural networks in practice, namely how to set the learning rate, the loss landscape being very complicated, and we may get stuck in the local minima, and this notion of overfitting, and important considerations for neural network training. So I hope that gave you sort of a flavor and fundamental ideas behind what neural networks are and how they're designed, trained, and what you should be considering. In my opinion, to understand everything else in the course, this is pretty much enough. But if you want to do this in practice and try to connect the dots, you can also check out a demo that kind of illustrates this in PyTorch on the course website. The link is over here. Look for demo 1 next to this lecture's slides, and you can follow the Python notebook there and kind of connect the dots with whatever we have covered in this lecture. All right, so with that, we'll end the lecture for today, and thank you very much for your attention.